Ladies and gentlemen, welcome to Monster Chemistry Review 2014! In this box right here, we have questions from everybody in the class that we'll be answering over the course of this period. First thing I want to do is give this box a good shake. And then grab a question. Our first question of the 2014 Chem Review session is, how can you identify an acid or a base? Whoa! There we go. Reference tables K and L will give you the various formulas of the common acids and bases. Notice that all acid formulas begin with what? H. With the exception of ethanoic acid written like this, anything that ends in COOH is an organic acid. Bases all end in what? OH, with the exception of NH3 aqueous, which when dissolved in water forms NH4OH. So if you run into problems with identifying acids or bases or naming them, reference tables K and L will give you all the information you need with regards to that. Acids have a hydrogen, hydroxide for a base. Anything else? That'll work. Oh, last minute question. Okay. Anything else on that one? Right then. Time to choose another question. Here we go. Second question.
Excuse me, Mr. Reisner. There's a student taking quarterly apples, so I'm just going to shut you down.
That's fine. We'll edit that out. Okay. How do you find the pH of a molecule? Well, you can't find the pH of a molecule. What you can do is find the pH of a solution of an acid or a base. Molecules by themselves do not have a pH. They need to be in solution for that to happen. You will not be asked to calculate the pH of a solution, but what you will be asked to do is to know that a pH of 1 compared to a pH of 2 compared to a pH of 3, this is 10 times more acidic, or has more H plus or H3O plus as a pH of 2. And 100 times more acidic, or having H plus or H3O plus, than a pH of 3. Every pH you change by, every pH number you change by is a 10-fold change in acid or base strength. Going lower, you get 10 times more acidic. Going higher, you get 10 times more basic. You will not actually be required to calculate the pH of any particular solution. Okay. Anything else on this? Right then. Third question. Write the formula for phosphorus 4 oxide, and why is it that? Okay. There are two ways to write the formula for phosphorus 4 oxide. First of all, phosphorus 4 has a charge of +4. The stock system, the Roman numeral, tells you the charge. Oxide is O minus 2. Now you can do the empirical formula, which is the simplest whole number ratio of the ions in the compound, or in this case the nonmetals in the compound, in which case you would get a formula of PO2. However, because both P and O are both nonmetals, they also can form a molecular formula, which would be an unsimplified, an unsimplified formula. You can only do this with covalently bonded nonmetals. You can have both an empirical and a molecular. If you've got an ionic bond, it can only be empirical. So for example, if we had Pb plus 4 and O minus 2, the formula would have to be PbO2 and could never be Pb2O4. Ionic compounds consisting of a metal and nonmetal must always be empirical. Anything else on that? Sure.
If you put PbO,
PbO2 is exactly what you want.
oh,
Yep. Now again, it's going to ask either it's the molecular formula or the empirical formula, but they'd never ask you for the molecular formula for Pb and O. Or Pb and J, for that matter.
oh.
Okay.
Okay.
Next question. What substances form ethers, esters, and ketones? Okay. Let's take a look at that table, which is table R on the reference tables. Ethers, esters, and ketones. Okay. Ethers are simply organic compounds where you've got two carbon chains surrounding a single oxygen. In other words, there's an oxygen with stuff on either side of it. All right? Exactly. Now, to form an ether, you need two alcohols. When you combine the two alcohols together, the H of one alcohol and the OH of the other alcohol are removed, and the two molecules join together to form an ether, as in if we were to take, let's say, methanol and react it with ethanol, using a sulfuric acid catalyst, the H of one and the OH of the other are removed, and that forms water, and the two molecules join together where the water was removed to make methyl ethyl ether. Now, that's how to make an ether. To make an ester is almost exactly the same reaction, except instead of taking two alcohols, you take an organic acid and an alcohol. The H and OH are removed, and you end up with an ester. Now the problem is, we can't call this methyl ethyl ester, because if we did, we'd have no idea which chain, the one carbon chain or the two carbon chain, the double bonded, bless you, the double bonded oxygen is on. The double bonded oxygen is on the side with only one carbon. So the name of this would be ethyl, because that's the side without the oxygen, methan O8. That O corresponding to the double bonded oxygen in the molecule. To tell you it's on the side that only has one carbon, meth, on it. Ethyl methanoate. And as far as how you make any of the other kinds, you will not have to know that for the Regents. The Regents does not ask you about the synthesis of any of the other families besides ethers and esters. If you take college organic chemistry, that's when you'll get into that. Any other questions on that one? Alrighty. Next one. Anonymous. What's this? It's a moose with its turn signal on.
That's waving. Yeah, I think you're waving too.
What's this? Exactly. Moose with its hazards on. What's this? This. Exactly.
Oh, I thought, so it's like, oh.
Okay. When are brackets and charges drawn with dot diagrams? Okay. The giveaway there is charges, because to have a charge, what kind of bond do you have to have? Ionic, because ions are charged particles, and ions form ionic bonds. So here are two circumstances for dot diagrams. For example, let's say we have sodium fluoride as one example, and hydrogen fluoride as our second example. Sodium is a metal and fluorine is a nonmetal, making this bond ionic. So you're going to draw the Na in brackets with its charge outside, and the fluorine in brackets with 8 dots to show the stable octet that fluoride gets when it forms an ion. And that would be the dot diagram for sodium fluoride. But hydrogen fluoride is made of a nonmetal and another nonmetal, which makes it covalent. And covalent bonds involve sharing a pair of valence electrons to form a covalent bond. And that would be the dot diagram showing an electron shared from hydrogen and another one from fluorine to make your covalent bond. So that's when you would use the charges and when you would not use the charges. Would you like more examples of this?
Yes.
Okay.
Wait, don't always
Okay. Okay, so instead of NaF, let's suppose we were going to do calcium fluoride, CaF2. So exactly the same thing would take place, except calcium has a charge of +2, and how many fluorines do we need in the formula? And we put the second fluorine on the other side of the calcium. And the reason for that is they're both attracted to the calcium, but they both repel each other because they both have a -1 charge. Instead of HF, we'll do H2S, which was the example from that last Regents exam that we tried. And that would be the dot diagram. Now I know there would be the idea that, oh, we should just put them straight across, but here's why we wouldn't do that. Sulfur has 2 unpaired valence electrons, and they're here and here. So wherever the unpaired valence electrons are, that's where your bonds are going to form. What shape is that, by the way? It's not linear, it's... What's my arm?
Or angle.
Bent!
Oh.
So what were the other shapes? For example, what shape is that? Yes?
Oh my gosh.
The shape is pyramidal. That's right.
Pyramid.
Pyramidal. And if it was like this, it would be tetrahedral. Exactly. Okay. Linear, bent, pyramidal, tetrahedral. I could get my arms to bend in that, but they just don't do it.
Bend. And then what? Wait, what's the first one? Horizontal? Linear.
Linear, bent, pyramidal, right? It's like 3-sided, right? And tetrahedral, straight across. As long as they're at a right angle, doesn't matter where you put them. Remember, with dot diagrams, it doesn't matter what side you start dotting them from, as long as you put 2 dots on the first side and then start going around with 1. Yep. Good. This turned out to be an excellent question. Thank you. Anonymous. Anonymous. Exactly. Okay, next question. How does one do carbon chains? I didn't know it was a dance. I'm not quite sure what the question is asking, so what I will do is, if the person who wrote the question wants to clarify, if not, I'll just have to make my best guess. No? Okay. carbon bonds to itself to form chains, and there's no end to how long those chains can be. You can have simple one carbon molecule, which would be methane, all the way up to molecules that have thousands or even millions of carbons bonded together in a chain to make polymers. There are three kinds of hydrocarbon chains. And again, we're just doing hydrocarbons here. There are alkanes, where all the carbons are bonded together with single bonds, which, by the way, would be considered a saturated hydrocarbon. Because the only way you could add anything else to this molecule would be to pull off at least one of the hydrogens and replace it with something else. There's no double bonds that can be broken to just simply add, so it's a saturated hydrocarbon. You can also have unsaturated hydrocarbons, where you don't have to remove hydrogens to add to the molecule. All you have to do is break a double bond and you can add directly to the molecule. And these would include alkenes and, of course, alkynes. These would both be unsaturated. Because if you react this with something, you don't have to pull a hydrogen off. You can just break the double or triple bond and just add right to the molecule at that point. This would be 1 pentene, this would be 2 pentyne. The number indicating how many carbons in from the shortest end you have to go before you reach the feature that the thing is named for. Question? These alkene and alkyne. Okay? If it's all single bonds, it's an alkane. If there's a double bond, it's an alkene. If there's a triple bond, it's an alkyne. And if there's multiple bonds, that means it's an unsaturated hydrocarbon. What if there was fluorine? Would it still be considered a hydrocarbon? No. With fluorine, it is now considered to be a halocarbon, absolutely, because it's angelic. A halocarbon. All right, anything else on this? I'm not sure if that's what they were asking, but hopefully it was. Yeah, okay. I was just hoping it was recording, and it is, so that's good. Okay, next question. Review math problem that you solve in math.
Yeah.
I'm going to assume that the person who wrote this, I have no idea what they meant. What did it mean?
I'm trying to say, like, go over the math, like how do you use the math formulas in the math
Okay. Here's something to keep in mind at all times.
No.
Guys, something to keep Gesundheit in mind at all times. Gesundheit again. All of your math formulas that you will need are already on reference table T. What you have to do is take a look at the information you have and determine exactly what you need to use. For example, if it says to find the percent composition of by mass, then you just take the mass of the part divided by the mass of the whole times 100. If it says find the molarity of the acid and it gives you stuff about the base too, then you have to use MOVI equals MOVA. You just plug it in. They're either going to ask you just to plug the numbers into the equation and just leave it there, or they're going to ask for an actual completed answer. And sig figs up to this point have never been an issue on the Regents exam. It's like accept the correct answer regardless of how many sig figs they have. Which kind of makes me a little annoyed because we spend so much of the year dealing with significant figures, but it's the way it is. You guys will be ready for when you go into, college science classes. But again, for example, it says calculate the molarity of this, and it gives you like how many grams and how many liters or whatever. Well, that would be moles equals given mass divided by gram formula mass to get your moles, and then you would use molarity equals moles divided by liters to get your molarity.
I don't want like the MC delta T. Like what?
Well, again, MC delta T, let's see, where is that? Oh, it's all the way down here, okay. MC delta T is an equation that's used to find out how much heat it takes to heat something up or cool something down, how much energy it takes to do that. And what you do is you take the mass that they give you, the mass of water that you're heating up or cooling down, multiplied by the specific heat capacity of water, which is essentially how fast the water heats up or cools down. You can find that on the front of your reference table. The specific heat capacity of water is 4.18 joules per gram Kelvin, or Celsius, doesn't matter, you can use it for either. And then delta T is how much does the temperature change by. And they'll either tell you how much it changes by, or they'll say it starts at this temperature and it ends at this temperature. And that's really all it is. Yeah, the math on the regions is actually really easy. It's insanely easy. Just don't overthink it. Oh, and one other thing. They used to have this on the reference tables. They got rid of it in 2011. The temperature per gas laws has to be in Kelvin, and down here they give you how to convert. Yep. Is there anything else? Was that what you were looking for?
Yeah.
Okay. Okay, next question. How do you have a space party? Well, first you go to Fargo, North Dakota, to Space Aliens Bar and Grill. You order food, which is extremely greasy, hope it shows up before you have to leave, and then just party! Either that, or you find the empty space in between molecules in a gas, and you just set up there and you know, find a DJ, although you won't hear anything because in empty space there's no medium to conduct sound. So you can just leave the DJ at home.
Or
just
you can plan it.
BYOO, bring your own oxygen. Or you can plan it. Nice. Next question. What is it called when you decrease pH? Example, pH 1 to 2 is tenfold. What is pH 2 to 1? It's also tenfold. We've already gone over this one. Essentially what it goes down to is this. pH of 1, pH of 2. pH of 1 is 10 times more acidic. And pH of 2 is 10 times less acidic. Or you could say 10 times more alkaline. Or basic. So as you go down in pH, you become more acidic. As you go up in pH, you become more basic or alkaline. Was that more or less what was wanted? What? A pH of 7 is neutral. A pH of below 7 is acidic. And a pH of above 7 is basic. Okay? Therefore, if you're going towards the lower numbers, it's becoming more acidic. All right? But if you're going towards the higher numbers, it's becoming more basic. Yeah. This is the pH at which you have an equal amount of H and OH. And by the way, because all these contain H plus ions, all acids conduct electricity. They're all electrolytes. And because basic all contains OH minus, they're also electrolytes. Because an electrolyte is anything that dissolves in water and gives off ions that can conduct electricity. So both acids and bases are electrolytes. you guys a moment to get that down, if you like. Hello? Hello? You know, I'm gonna have to watch this whole thing all over again. I'm gonna have to sit through the whole thing and just like make edits to it. And I'm not only recording your class, I'm recording period 4. So.
I think we should.
You don't want people hearing about the space party?
Oh no, I'll keep the space party in there.
I love period 4.
Anyone need more time? Anybody have any additional questions? Next question. Review of reference table M, how to tell what color each indicators will turn. Very good. Okay. So let's have a look at reference table M. Okay. Essentially what it's saying is this is the approximate pH range for the color change. In other words, between 3.1 and 4.4, it's turning from red to yellow, but in this range, it's actually orange. Any pH that's this or, and it's kind of is it this or lower, or is it lower than this? They're not actually going to put you on the spot like that. They're going to make it very clearly definitive one way or another. They're not going to say what color is methyl orange at a pH of 3.1. They're not going to do that. At a pH of 2, what would methyl orange be? Red. And at a pH of 10, what would methyl orange be? Yellow. That's really all you have to do. Or it might say, what color is brome cresol green in a base? Blue, just like it was on that exam. Right? Anything that's above 5.4 is going to be entirely blue. This is the range at which it gradually turns from yellow to blue through green. Maybe not the best way to make this table, but it works. Is that what was being looked for here? Maybe? Okay, sounds good to me too. Next question. Review stoichiometry.
Oh boy.
Okay, yeah, that's just a very, very tiny thing there. Okay. It actually is, because stoichiometry on the reagents is limited to 2 things. Being able to convert grams to moles and moles to grams using formula mass, and doing simple mole-to-mole stoichiometry. So, for example, if we have a reaction like, I'll put up our old favorite, N2 plus 3H2 forms 2NH3, a question might say, for example, how many moles of NH3 are formed when 5.0 moles of N2 are completely reacted with H2. And all that last part means is just a disclaimer saying you don't have to worry about H2, we have enough H2 to get the job done. And, I mean, you don't even really have to do much in the way of math. I mean, it's a 1 to 2 ratio, so if we've got to make 5 moles of this, how many moles of this are we going to need? Well, it's a 1 to 2 ratio, right? So whatever NH3 is, N2's got to be half that, because it's a 1 to 2 ratio, right? So if I want to make 2 moles of this, I need 1 mole of that. And if I want to make 5 moles of that, I need 2.5 moles of N2. Exactly. If you want to set it up mathy-like, here's how you would do it. You would say you've got 5.0 moles of N2. Oh, I'm sorry, I did it the wrong way, didn't I? We have 5 moles of this, so how many moles of that should we get? 10. Okay, you were right. All right, so 5.0 moles of N2, and then we multiply it by the ratio of NH3, which is what we're looking for, and N2, which is what we have, so that it cancels out. And then we just plug in the coefficients. What's the coefficient of NH3? 2. And what's the coefficient of N2? 1. So 5 times 2 over 1 would be 10. That's as far as they're going to take it on the regions. That's as far as stoichiometry goes. Now in class you had to convert grams to moles, multiply by the ratio, and then convert moles to, let's say, liters or molecules. You won't have to do that on the regions. On the regions it's just a straight, it's a 1-to-2 ratio. If I got 20 of these, how many of these am I going to get? 40. Think of it like a recipe. All right, one mole of this and 3 moles of that will give you 2 moles of that. So if I want to make 4 moles of this, 4 moles, twice as much, I'm going to need 2 of these and 6 of these. You're just doubling the recipe. If I want to make 1 of these, then we need 0.5 and 1.5 of these. It's just a simple proportion. That's it. Any questions? Yes, sir?
Why is it 2 over 1?
Okay, when you're setting up a proportion, you want to take the thing that you're trying to get rid of because you know it, right? Put it on the bottom so that it cancels out. The thing you're trying to solve for goes on top. It's like any conversion factor that we've done all year. So for example, if we've got grams and we've got grams per mole, if we divide that, the grams will cancel. But if we have moles and grams per mole, then we multiply it to cancel it out. So when you multiply by a conversion factor, the unit you have will cancel out the denominator if it's the same unit. If you multiply this by 1 over 2, then you're going to have N2 squared over NH3 as your unit.
Why is the coefficient of 2?
The coefficient of NH3 is 2, and the coefficient of N2 is 1. So you just use the coefficients from the balanced equation to put it in there. That's all. That's all you have to do. Any other questions about this? Yes?
On the regions, are you going to have to find the balanced equation?
No, the way it works on the regions, they used to have like multiple part questions, but they're either going to ask you to balance it, or they'll give you something that's already balanced and you've got to do the stoichiometry. Typically, this is going to be a part B2 or C question, and the balanced equation will be part of a description of, for example, you know, this is the process that makes ammonia. Ammonia is used for blah, 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 and a whole bunch. This would just be one question in a series of questions. But each question is independent. They won't ask you to balance it and then ask you to do the stoichiometry. Because the way the regions is set up, an answer to a question cannot be dependent on the answer to any other question. All questions have to be independent on the regions. Yep, so you won't have to worry about that. Yep. Anything else? Yeah, that's all there is to it. Stoichiometry on the regions is as easy as it gets. Do you want another example? Yep, okay. All right then, next question. Ooh, a strip. Why are you such an awesome person?
There's 100 for this class on the regions.
You see, I don't grade your regions, so flattery isn't going to work here. But I thank you, whoever wrote the notes. Oh, hell no. Yeah, yeah, it's been a disaster. No, I put a little bit back on. It's horrible.
I think you should just take the classes last and just be like, 100. Oh my gosh. Oh my
I
gosh.
could lose my job doing that.
They don't have to know what's your class.
You know what the best way to get 100 on this test is? The best way to get 100 on the regions is to get every question right. Steve, this is being recorded, you know.
Is it true that if somebody in your class dies or kills themselves, you don't have to take it?
No, that's in college.
Oh!
No, that's in college. Who are you going to kill?
I don't want to. Stop for a point. Stop for a point.
Seriously, you would kill somebody just to get up.
This test is hard. As long as they were in all my classes and I would take any of them, then yeah.
Alright, so let's take how many times are they going to kill themselves so you don't have to take regions?
Okay, next question.
Kill themselves once. We can get out of time. I'd rather kill someone like
What are Arrhenius acids and bases? They may ask you Arrhenius by name, but they're not going to ask you to spell it or anything. They might say, which of the following is an Arrhenius acid? And again, I refer you back to reference tables K and L. Arrhenius acids are anything that dissolve in water to give up H plus as the only positive ion in solution. And an Arrhenius base is anything that dissolves in water to give off OH minus as the only negative ion in solution. And that's what the definition of an Arrhenius acid. Acids have a hydrogen, hydroxide for a base, and we dissolve in water. The H is the only positive ion, and the OH is the only negative ion that there is in the solution. That does crop up quite a lot. Next question. Yeah. Question. How do you name the organic compounds? Well, usually you name them after family members. So, for example, maybe like from Uncle Bob, you name him Robert or something. I don't know. How do you name organic compounds? You basically use reference tables P, Q, and R to name organic compounds. Very straightforward. Reference table P is how many carbons are there in the main chain of your molecule. Meth, eth, pro-but, pent, hex, hep, doc, non, dec. If you've got a hydrocarbon, then it ends in ane, ene, or ine. So, for example, methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, or there's no such thing as methene, ethene, propene, butene, pentene, hexene, heptene, octene, nonene, decene. For alkynes, it would be ethine, propine, butine, pentine, hexine, heptine, octine, nonine, and decine. You would also have to put a number before the name to say how many carbons in from the end your double or triple bond are. So, for example, in this molecule here, this would be but because there's 4 carbons, ene because there's a double bond. How many carbons in from the short side is it?
1.
Exactly. You only have to go 1 carbon and whoa, look at that, there's the double bond. Yes, sir?
Missed one of the hydrogen.
Ah, good call. Okay, you do not have to draw the hydrogens, but you do have to draw the bonds, so I would not have gotten 100 on the regions. I know.
Man.
Now, if you've got anything other than just hydrogen or carbon, the naming is going to depend on reference table R. And reference table R tells you how to name these molecules. If it's an alcohol, it ends in anol, and you got to put a number in front to say where the OH is. If it's an ether, you name it for what's on either side of it. If it's an aldehyde, it ends in anal. If it's a ketone, anone, and you have to put a number in front to say where the double bonded oxygen is. If it's an organic acid, anoic acid. If it's an ester, you name it for the side without oxygen, and then for the side with oxygen. And for amines and amides, they end in amide and amide. I mean, it's pretty straightforward. So, for example, if I had this molecule here, double bonded oxygen in the middle of the molecule would make it a ketone. And since there are 4 carbons, it would be butanone. And since the reference table tells me I need to put a number in front to say where the double bonded oxygen is, this would be 2-butanone. And that would be how you would name an organic compound. Very simple, very straightforward. Use reference tables P, Q, and R together. Look at the examples they give you on table R, and that will seriously help you out. Anything else on this? Yes?
How do you mean like the ethers and esters?
Okay, again, the ethers and esters are named for what's on either side. So, for example, ethers always end in ether, right? So, let's say we've got 2 carbons on this side, and we've got 3 carbons on this side. The prefix for 2 carbons is eth, so this would be ethyl. The prefix for 3 carbons is prop, so that would be propyl, ethyl, propyl, ether. Okay? If it was an ester, then you have to name it based on what side does not have the oxygen, double bonded oxygen, and what side does have it. So the name of this would be propyl ethanoate. because the side without oxygen has 3 carbons, propyl. The side with the double bonded oxygen has 2 carbons, ethanoate. And you know it's ul-anoate because that's what it says right here, ul-anoate. You just use the pattern, just put prefixes in as they're appropriate.
Okay.
Yep. Up until 2000, this table wasn't even available. You had to memorize all this stuff.
Okay.
Yeah. Okay. Let's suppose we had an alcohol. Let's say we wanted to have 2-propanol. Okay, 2-propanol. That means that as an alcohol, we have to bond OH to the second carbon. The question is, do we bond the carbon to the hydrogen, or do we bond the carbon to the oxygen? Well, it's pretty easy to determine that. Hydrogen only has 1 valence electron. Oxygen has 2 unpaired valence electrons. If you bond hydrogen here, then you're done, because hydrogen can't bond to anything else. So if you bond the carbon to the hydrogen, there's nothing else you can do. But if you bond the carbon to the oxygen, that leaves another space for the hydrogen to bond on. So the O gets bonded to the carbon, not the H. And when you draw the molecule, you have to be very clear about the carbon bonding to the O and not the H.
Yeah, I got that wrong.
Exactly. Anything else? Okie dokie. Okay, next question. Oh, we still have quite a few. Next question. What is the difference between using Q equals mc delta T, Q equals mass times heat of fusion, Q equals mass times heat of vaporization? Excellent. Okay. Let's suppose we start with a solid below its freezing point and add heat to it at a constant rate. As we do that, the temperature will rise as the molecules in the solid begin to vibrate faster. But eventually you'll get to the point where the molecules are vibrating so fast that they can't move any faster unless you weaken the attractive forces between the molecules. And at that point, the substance melts. And during the melting process, all the energy that goes into it doesn't go into heating it up, it goes into breaking those attractive forces, or at least weakening them to some degree, so that the molecules can slide past each other and form the liquid phase. Eventually, you can heat a liquid up to a certain point, but eventually you'll get to the point where if you want to make the molecules move any faster, you'll have to first break the rest of the attractive forces to make that happen. And that's when boiling takes place. And then eventually, once all of the liquid has been boiled away, any additional heat will make the molecules move faster. Gradually you'll hit plasma and all the rest of that, but that's as far as we have to take it. Solid, liquid, gas. Now, during any point where the temperature is rising, we have a delta T, a change in temperature. So to find out how much energy it takes to make that happen, we use Q equals mc delta T. How much mass are we heating of solid? What's the specific heat of that solid? And how much is the temperature change to get from where we started to the melting point? At the melting point, we're trying to add energy to melt it, but is there a delta T? No, there is no delta T. So we use Q equals mass times heat of fusion. The energy that goes in does not go into changing the kinetic energy, it goes into changing potential energy, heat of fusion. Temperature is measured in Kelvin, kinetic energy. Heat of fusion is measured in joules, which is potential energy. When it's a liquid, the molecules are moving again, and again we have a change in temperature. So we can use Q equals mc delta T. The specific heat of the solid and the liquid are always different. You will not have to worry about that on the Regents exam, or at least we've never had to worry about it before. When we get to the boiling point, once again, there is no change in temperature, so we use Q equals mass times heat of vaporization this time, since we're turning our liquid into a vapor. And again, while it's a liquid, we're changing kinetic energy, which is why delta T gets used. During the phase change, temperature doesn't change. We're changing the potential energy. That's why we use heat of vaporization. And again, for gases, we can use Q equals mass times MC delta T. You guys actually had an activity early this year where I said, determine how many calories it would take to heat water from minus 15 degrees Celsius up to 110 degrees Celsius. I had to work out all 5 of the steps. Do you guys remember that incredibly horrible activity? Right? Then you had to divide it by how many minutes it took to get the joules per minute and all the rest of that. Yeah, you won't have anything like that on the Regents. They're going to ask you either for MC delta T, or for heat of fusion, or for heat of vaporization. It won't all be in the same problem. Any additional questions with this? Yes, ma'am. Exactly. Temperature is measured in Kelvin, which is kinetic. Yep. This is called the heating curve chart.
It's not the one what's like the
Right, the PE diagram is a different chart. It's very common when people, when there's a question on the Regents, draw the PE diagram for, and people will draw this chart, but this isn't the PE diagram. It's a KE diagram of a phase change, so you wouldn't want to use this. Any more questions? Well, if we have time, if we get through that. Okay. All right. Write that down and put it in the box. Write that down and put it in the box. Write down and put it in the box. Okay. Next question. What is the percent by mass of water in choose a compound .3H2O? Okay, cool. That'll work. Does anybody need more time for this? Right? Okay. Let's say we have the hydrate, let's say calcium carbonate .3H2O. I doubt that's actually trihydrate, but it doesn't matter for the purpose of this. Okay. To find the percent of water, percent is always found as follows. Da-da-da-da-da. Percent is mass of part divided by mass of whole times 100. In this case, we don't have any masses. We have to use the gram formula mass of these things. Calcium's atomic mass is 40.1. Carbon's is 12.0. Oxygen is 3 times 16.0, since there are 3 of them. Water weighs 18.0, 2 for the hydrogen, 16 for the oxygen, and there are 3 of them. And that would give you your total formula mass. Let's add all that up. So we have 18 times 3, I'll start with that, plus 48 for the oxygens, plus 12 for the carbon, plus 40.1 for the calcium, gives us a total gram formula mass of 154.1 grams per mole. The formula mass includes the water. So the percent, the 154.1 is going to go on the bottom. That's the mass of the whole. The mass of the part is the mass of the 3 waters. Okay? And what's 3 times 18 again? 3 times 18 is 24. And that will give you your percent by mass of water. You have to make sure to include the part in the whole. It's sort of like saying if I'm weighing my car and my seat that I'm sitting on that I'm trying to get the percent, like what percent of the mass of your car is the passenger seat of your car? That would be like saying, okay, I'm going to weigh my car and And take the passenger seat out. All right, take the passenger seat out, weigh that, then weigh the car without the passenger seat. No, you want to weigh it with the passenger seat because it's part of the car. So part over whole times 100. The most common mistake that's made, here are the two most common mistakes. One is just putting 18 in the numerator, just saying, oh, the water is 18, but there's 3 of them, leaving that out. And the second most common mistake is not doing the formula mass for the whole hydrate, only doing it for the part that doesn't have water. So it's part over whole times 100. Any questions on that? Okie dokie. Next question. Could you go over hydrogen bonds? Hydrogen bonds! Absolutely. What's that? No, I made one. Okay, anybody need more time with this? Okay, hydrogen bonds. There are 2 main kinds of bonds that form compounds, covalent bonds and ionic bonds. Hydrogen bonds are not chemical bonds. What they are attractive forces between the positive end of one molecule and the negative end of another. For example, in a water molecule, hydrogen is covalently bonded to oxygen, and another hydrogen is covalently bonded to that oxygen. But the bonds themselves are not polar. Oxygen has an electronegativity of 3.4 and hydrogen is 2.2, meaning the electrons from each bond pull towards oxygen, making the oxygen end of the molecule partially negative and the hydrogen end of the molecule partially positive. If another water molecule were to just happen by, okay, the partially positive hydrogen end of one water molecule will attract very strongly to the partially negative end of the other water molecule. Extremely strong attraction, which is what allows insects to walk across the surface of water, or to allow you to overfill a cup of water until you have a meniscus on the top. The same attraction that causes a meniscus in a test tube or graduated cylinder. Water's natural attraction for itself. And this attraction is called a hydrogen bond. And it will form in any molecule where the H side of one molecule bonds to the NO or F, because these have such high electronegativities, end of another molecule. Hydrogen bond. H on one side, NO or F on the other, hydrogen bonds! Hydrogen bonds! That was loud enough. Any further questions on that? Okay. Next question. Molality review, please. Molality review, please. Easiest review ever. Molality, not on the regents.
Yes!
Next!
Yes! One last thing I need to know.
How do you determine polarity? Well, we've kind of just done that. And again, the question becomes, are you talking about the polarity of the bond or the polarity of the molecule? Because they're 2 completely different things, even though they are related. I'm going to use a different example other than water. I'm going to use a bond between carbon and chlorine. Now, according to reference table S, hydrogen has an we're not talking about hydrogen here. Carbon has an electronegativity of 2.6, and chlorine's electronegativity is 3.2. So 2.6 and 3.2. 2.6, 3.2. The difference in electronegativity between these 2 bonded atoms is 0.6. Anything that's higher than 0.4 would be considered polar, because the more electronegative end is going to pull electrons towards it. That would be a polar covalent bond. a bond between an oxygen and another oxygen is going to have an electronegativity difference of 0, making the bond nonpolar. So nonpolar covalent, polar covalent. Now let's take a look at the molecules in which these are found. Yes?
What's the, like, what does it mean if it's an electronegativity difference of more than 1.8?
Okay, electronegativity difference of higher than 1.7 is typically ionic. Now there is one exception to that, HF. HF has an electronegativity difference of 1.9. Actually, it depends on, let's see, 2.2, okay, 1.8. But it's still considered to be covalent, just wicked polar. Okay? The essential way of looking at it is if you've got a metal and a nonmetal, it's ionic no matter what the END is. If you've got two nonmetals, it's covalent regardless of the END. If the electronegativity difference is 0.4 or less, then the difference in pull isn't strong enough to give you poles, so it's nonpolar. If the difference is greater than 0.4, that means one side is getting the electron more than the other side is. So that's why we call it polar. Now if we put these into molecules, let's suppose we make a molecule of carbon tetrachloride or tetrachloromethane. We've got 4 polar bonds. The electrons are being pulled towards chlorine in each of these bonds. But these bonds geometrically cancel each other out. The pull in this direction is canceled out by the pull in that direction. The pull in this direction is canceled out by the pull in that direction, meaning that the entire molecule has a symmetrical distribution of electrical charge, making the whole molecule nonpolar. In the case of water, hydrogen has an electronegativity of 2.1, oxygen is 3.4, so in a bond, in a molecule with water, electrons are being pulled in both bonds towards oxygen. There's nothing on the other side to cancel this out, so you could say that this has an asymmetrical distribution of charge. This is symmetrical, and this is asymmetrical. This is a nonpolar molecule. This is a polar molecule. Yeah?
So on the regions you're asking what type of bond is HF?
It won't ask you what type of bond is HF. They'd ask you what type of bond holds an atom of H to an F, or what kind of bond is found in a molecule of HF. Your only two choices are ionic or covalent. You can go further with polar covalent and nonpolar covalent. Typically what I've seen as acceptable answers on the regions is polar covalent and covalent would be acceptable. They don't always say that you have to put the polar afterwards, especially if it's such a general question like that. Now they may ask a question in multiple choice, which of the following bonds is which of the following molecules contains a nonpolar covalent bond? Then you'd have to look for the one with an END of 0. What's that? What kind of attractive force, usually they'll say strong attractive force, is found between two molecules, and the molecule is going to have H on one side and N or F on the other. The only kind of attractive force the Regents is going to ask you for is hydrogen bonds. It's the only one you need to know by name. You don't have to worry about dipole or London dispersion or any of that. Yep. Just hydrogen bonds. They keep it simple. Anything else? Next question. How can you convert moles to grams and milliliters to liters? Okay. They're different, but they're actually identical because they both rely on conversion factors. And we've been kind of going nuts with conversion factors all year long. You've got grams per mole, you've got milliliters per liter. And all you need to know is how many you have. How many milliliters are in a liter? There's 1,000 milliliters in a liter. Okay? The number of grams in a mole depends entirely on the formula mass of the substance. Water is 18, sodium chloride is 58.5, it depends on the substance. If you've got grams and you want to convert grams to moles, we have to divide so that grams cancels out and leaves us with moles. But if we've got moles and we want to get grams, we have to multiply to cancel out moles. Now it's exactly the same thing with milliliters and liters. If we've got milliliters, since milliliters is in the numerator, we have to divide to get liters. But if we have liters and we want to get milliliters, since liters is on the denominator, we multiply to cancel it out. So what you do is entirely dependent. Are you looking to solve for the numerator of your conversion factor or the denominator of your conversion factor? If you're looking to solve for the numerator, then just multiply. If you want to solve for the denominator, divide. And it doesn't matter what your conversion factor is. Grams per mole, milliliters per liter, grams per cubic centimeter, doesn't matter. All conversion factors work exactly the same way. Any further questions on that? Okay. Next question. Oop, that's two questions. Here's one question. Half-lives! It's not really a question though, is it? Okay. Understanding how half-lives work depends on knowing the definition of half-life. We have on reference table N the half-lives of several different radioactive isotopes. This gives you the atomic mass of the isotope, this gives you how long the half-life is, this tells you how it decays, and so on. Half-life is simply defined as the amount of time it takes for you to have half the amount of stuff you have now. It can be used in medicine to determine how long it takes for medicine to be flushed out of the body. It can be used for radioactivity. It can even be used for some chemical reactions. How long does it take so that we only have half our reactants left? And every half-life, you have half of what you had the previous half-life. And the way the questions are going to be framed is going to be like this. Let's say we have 10 grams of CS-137 now. And it asks how many will be left. Um, 60.4 years from now. Okay? So the first thing we need to do is figure out how many times did we have to cut cesium-137 in half. So we take the amount of years and we divide it by how long each half-life is, which is 30.2 years. So how many half-lives are we talking about? 2. Okay. So what we do is we take our 10 grams and we cut it in half. Whoops. We cut it in half twice. So in the first 30.2 years, we're going to bring it down to 5.0 grams. And in the second 30.2 years, bringing us to a total of 60.4 years, that'll bring us down to 2.5 grams. It can also say how many grams were there 60.4 years ago. In which case, you're going to go back in time. So one half-life ago, we would have had 20 grams, and the half-life before that, we would have had 40 grams, just working our way backwards. So a half-life is simply how long does it take for the amount of substance you have to be cut in half. And you always start at 0. Any other questions on this? Okay. Bonding. We already took care of that, kind of. So we'll just do another little look through bonding. 2 kinds of bonding, ionic and covalent. If you've got a metal bonded to a nonmetal, the metal will give up its valence electrons to the nonmetal. the metal becomes positive, the nonmetal becomes negative, and they attract and form an ionic bond. If you have two nonmetals, the nonmetals are going to have unpaired valence electrons that they can share with the other nonmetal. So that's what they simply do. They share their unpaired valence electrons, and that pair of shared valence electrons is called a covalent bond. And that's really all there is to ionic bonding and covalent bonding. That's it. Transfer of electrons, sharing of unpaired valence electrons. Probably could have saved a lot of time if this is all I did when we did this unit, but. Anything else on this? Okie dokie. Next question. Can you explain, and demonstrate the difference attractive forces like dipole, van der Waals, atmosphere? And the answer to that question is, you don't have to know any of them except for hydrogen bonds.
I really just don't.
Next up. This one is really squished up. Can we take a class selfie?
Yes!
Oh, I love you.
See why not?
Yes!
We will have a little bit. Should have a little bit of time at the end that we can do that. I don't know.
Who offered the selfie?
Okay.
Who was it?
Next question.
All flop.
Heat of reactants chart. Now, there's actually no such thing as a heat. Guys, there's no such thing as a heat of reactants chart. It doesn't exist. What there is a potential energy diagram that contains heat of reactants in it. Any chemical reaction is going to start with reactants and end with products. And there's either going to be an overall gain in energy, or there's going to be an overall loss of energy during the change. You measure the amount of potential energy versus time, also known as the reaction coordinate. There are three levels of energy that can be found in a potential energy diagram, the highest of which is the heat of the activated complex, which is the point you've got to bring the reaction to for the bonds to break. It's the amount of energy that's got to be there for the reaction to take place. If it's an exothermic reaction, you're going to start with more energy than you end with. You only have to put in a little bit of activation energy, and you lose potential energy, a negative delta H. That would be exothermic. Delta H is also known as the heat of reaction. Not to be confused with the heat of reactants. In other words, the overall change from where we start to where we end. And you can make it take less energy and time simply by adding a catalyst, and a catalyst will lower the activation energy so that it doesn't take as much time or energy to take place. An endothermic PE diagram simply looks the opposite of this. We start low and we end high, going through the activated complex. Yes?
What would the catalyst do?
A catalyst, do you remember the little demo I did where I had those funnels set up and I poured the water through? We timed how long it would take. Then we added a catalyst, we took away one of the funnels and we poured the water in, and because it was one less step, it took that much less time. Then we threw the inhibitor in, which was that tiny funnel on the top, and it took like forever, and I don't remember, did I pour for that or did somebody else pour for me? I think, and my legs are starting to shake, and it's like, ah, yeah, exactly. So a catalyst will lower the activation energy, and an inhibitor will raise it. And that's the same whether you have an exothermic or an endothermic PE diagram. Yeah? It will start here, which is now the heat of reactants, and will end up here. In fact, I'll just draw that in black for you. For endothermic, this would become the heat of reactants, this would become the heat of products, and your PE diagram would look like that. Wherever you start, that's the heat of reactants.
See, that makes sense. Now I get it.
I'm glad I went over it then. Yes, sir. Delta H is enthalpy. Think of it as there's an H in enthalpy, but there isn't one in entropy. So delta H is enthalpy. Exactly. Yes?
Never mind.
I only have 4 questions left. First one, is molar mass and gram formula mass the same? Yes. 3 questions. What? Oh, it was. I like these. So, gram formula mass and molar mass are the same thing.
What?
Deja vu. Yes. Next up. I think, quote, by Martin Luther King Jr. mean, when at hand in life, can you see good things in life? Life is, as you grow up, is your life going to better?
Oh, Baba. Classic.
3. Last question.
Is this one Baba's too? Because I'm going to laugh.
What is the difference between molecular formula, structural formula, and empirical formula? Excellent way to end it. Okay. Yeah. Okay.
Oh.
Here's the way it works. Let's suppose we've got a molecule of butane. What kind of structure would you, I'm sorry, I'm going to give away. What kind of formula would you say this was?
Structural.
Because it's showing you the structure of the molecule. This is structural. If we count up the number of carbons, 4, and the number of hydrogens, 10, that would be the molecular formula. But if we simplified it to its simplest terms, C2H5, that would be the empirical. And that's the difference between them. The empirical formula tells you the simplest ratio between the different elements. The molecular tells you how many atoms you actually have of each element. And the structural shows you how they're arranged in 3-dimensional space using a 2-dimensional representation. Sort of like if we were to draw a cube, this would be a 2nd-dimensional representation of a 3-dimensional object. This is a 2nd-dimensional representation of a 3-dimensional object. Or a shadow of the molecule, if you will.
Hello.
Alright, welcome to the second half, for those of you watching at home, of our Chemistry Monster Review. This is my Period 4 class! And I've come up with a bunch of questions to put into the Chem box. So what we're going to do is we're going to start off with the first and work our way all the way to the last. Now, you guys, as we're going through it, anything that I put on the board that you need time to write down, you just let me know so that we can make that happen. So, without any further ado, let's get to the questions. First question for this class is, what is the difference between molarity and molality? Very simple question. Molarity is moles per liter, and molality is not on the regents. Next question.
Which one's moles times liter?
Moles divided by liters. And if you take a look at reference table T, you will see on table T that molarity is moles divided by liters. TERS. I All right, next question. What just happened? What just happened?
Foul language was used.
Oh no, I'm not gonna edit it out. I'm just gonna make it louder so it's all count. Okay, this has 3 questions. Wow, that's cheating. Okay, I'll answer the first question, cross it out, put it back, and we'll reshuffle it. We'll get to it eventually. Question 1, spontaneous versus non-spontaneous. Here's the deal, okay? If I let go of this pen, which way is it going to go?
Down.
That's spontaneous. Non-spontaneous means the pen would have to go, and it can go up, but only if I constantly put energy into it. And that's the difference between spontaneous and non-spontaneous. There are 2 factors that determine whether a change will happen or not. They are called enthalpy, which we know as delta H, or change in potential energy, and entropy, which is also known as messiness, disorder, randomness, chaos, and so forth. Nature is lazy, which means overall there's a negative change in potential energy. And nature is messy, which means over time the amount of disorder will increase. Any change where this is true, for example, A solid forms B gas plus heat, is exothermic, loses heat, and goes up in phase, which means it goes up in entropy. This change will always be spontaneous. The opposite, if we have a gas, let's try that again, plus heat forms B solid. In this case, it's endothermic, it's a negative delta H, and we're going down in phase, which is a negative delta, positive delta H, negative delta S. Since both factors are unfavored, this would be an example of a non-spontaneous change. You don't have to worry about the delta G equation, delta G equals delta H minus T delta S, that will not be on the regions. Anything not on table T is not testable on the regions, unless they give it to you, and they've never given delta G equation. Okay, you just have to remember, if both factors are favored, spontaneous. If both factors are unfavored, not spontaneous. Okay. Any questions about that? Yes?
So can you just say, like, spontaneous is, like the way that the enthalpy and entropy have to be? Like, can you say it?
Nature is lazy and messy. Nature tends to like exothermic reactions that go up in phase. And the way it'll be like a multiple choice question, which of the following changes would be spontaneous? And they might give you some PE diagrams. So for example, this PE diagram might look like this, where you would have A solid and B gas. Okay, so you can see it was exothermic and went up in phase, so this would be spontaneous. And the other one might look like this, where this would be A gas and B solid. You can see it was endothermic, which is not favored, and it goes down in phase. So very often this is the way the question is asked. Okay, I can't guarantee you you'll have one there, but in case you do, this is typically how it's done. Okay, any other questions on this? We'll come back to the rest of those 3. Come on down, I welcome your question. Welcome. Thank you. Give it another shake. Alright, next question. This one has 4 questions on it. So again, I'll do the first, cross it off, and then move on. Spontaneous versus non-spontaneous. Been there, done that. Okay, fusion and fission. That one we can do. Okay. Fusion versus fission. Very simple. Fission means that you take a hook, you put a worm on it, you throw it in the water, and you hope you catch a fish. Fission, right. Now, it's when you take a big nucleus like uranium-235, hit it with a neutron, the atom basically explodes, splitting up into two smaller nuclei, like, let's say, barium and krypton, and 3 more neutrons are shot out, which can split more uranium-235s. That would be fission, splitting a big nucleus into 2 smaller nuclei. Fusion is where hydrogen is built into, whoa, I ruined it, into helium at a temperature of millions of degrees. And it has to be at a millions of degrees to get positive nuclei to move fast enough to fuse together. And that's fusion. Splitting apart is fission, putting together is fusing fusion. Hopefully that clears up the confusion about fission and fusion. Okay, anything else on that?
No.
Essentially, you're just going to have to be able to recognize them when you see them. Or it says, like, why is this an example of nuclear fission? And you have to explain, well, we're taking a big nucleus and we're splitting it apart into 2 small nuclei. Right, just very simple. Okay, next question. Explain the ground state and the excited state. Very good. Let's take, for example, oxygen, which has an electron configuration of 2, guys, which has a configuration of 2 6 in the ground state, which means that the nucleus, which has 8 protons in it, in the first energy level, we have 2 electrons. In the second energy level, we have 6 electrons. The excited state is going to happen when one of these electrons is moved to a higher energy level. For example, I might take one of these electrons here and move it up to here, making the configuration 1-7. That would be the excited state, and when that electron falls back down, it's going to give off light. And that's how light is formed. That's the difference between excited and ground. You do not have to worry about SPDF on the Regents exam. 1s2, 2s2, 2p6, right?
3s2, 3p6.
Should have been on the Regents exam. Yeah, that won't be there, and box diagrams won't be there either. Only shell configuration and dot diagrams. Okay. Next up. I'm missing. Okay, next question. What is plasma? There's solid, liquid, and gas, but is there plasma? Is fire a plasma? This is not on the Regents exam, but I will answer the question anyway. Solids, liquids, and gases are made of neutral atoms or molecules. You heat them up, but not enough to ionize them, not enough to pull electrons off. All elements have, and this is on the Regents, an ionization energy, which is the amount of energy it takes to remove the most loosely held electron from the atom. If you heat a gas up to the point where you've reached its ionization energy, it will lose an electron, and it's no longer a gas, it's now in a state called the plasma state. Plasma is essentially gas that's charged because the amount of heat you've given it exceeds the ionization energy. Is fire plasma? It depends on what you mean by fire. If you're talking about this kind of fire,
What about my case?
this is not plasma. And the reason it's not plasma is because in order for it to be plasma, it has to be heated from solid to liquid through gas. Fire is actually made of microscopic particles of solid carbon that we call soot. And in the heat of the reaction, the soot will glow a yellow, orange, or red color. However, carbon has an insanely high melting point, and so even the heat of the flame is not enough to even melt the carbon, let alone boil it. So fire is not a plasma, at least not from burning fossil fuels. There are certain flames which are plasma. For example, the exhaust given off at the back end of a rocket ship when the hydrogen and oxygen combine. It has to have a high enough amount of energy to actually strip the electrons away. We call that burst ionization energy, and that will be on the regions. So I was able to take something that wasn't on the regions and make it relevant to the regions and beyond. Okay, next up. What is the difference between nuclear fusion and fission?
Hey.
Did that. Been there, done that. Awesome. Next one. How do you find molecule to ion attraction? Well, you need a GPS and you need the coordinates and no. How you do it is actually in the name. A molecule would be like a molecule of water, and an ion would be just that, a charged particle. Now, in a water molecule, the oxygen end is partially negative and the hydrogen end is partially positive. So that positive ions can attract to the negative end of a water molecule, and negative ions can attract to the positive end of a water molecule. And that's molecule ion attraction. When a molecule of water is attracted to an ion, that's molecule ion attraction. Oxygen to the positive ion, hydrogen to the negative ion. It's a little bit more complex than what I drew up here, but for the purposes, it will do. Okay. Next question. Okay. Difference between exothermic and endothermic. Okay, very good. In all chemical reactions, energy is either gained or lost, and which one it is will tell you whether it's exothermic or endothermic. In all reactions, you start with a certain amount of potential energy called heat of reactants. Sometimes the reactants have a lot of energy stored in their bonds. Sometimes the reactants don't have as much energy stored in their bonds. Your energy is given to the reactants to turn it into what's called an activated complex, which is essentially where you get to the point where the old bonds can start breaking. We call this amount of energy activation energy to get to that point. From that point, the activated complex breaks down to form your final products. Oops. Sometimes your reactants have more energy than the products. Sometimes the products have more energy than the reactants. The total amount of energy that's changed is called the delta H, or change in heat, or heat of reaction. Not to be confused with heat of reactants, because they're not the same thing. In this case, it's a negative delta H since we've lost energy. In this case, it's a positive delta H since we've gained energy. This is exothermic, meaning heat is released to the outside. And this is endothermic, which means heat is taken into the system and stored as chemical bonds, or stored in chemical bonds. And that's the difference between exo and endo. This is favored, this is not. This is what you get when you blow something up. This is how you make the explosive. Use up the stored energy, pack stored energy in. It's Chainsaw Massacre Dude. Chainsaw Massacre Dude eats a candy bar, and then runs around chainsaw massacring. Anything further with this particular topic? Okie dokie. Next up. Describe these reactions: decomposition, synthesis, redox, ect. Oh, that would be ETC. Okay, this is ETC. Okay. Okay. The chemical reactions that we did, the non-organic reactions, were broken into two types: redox and ion exchange. The reactions were one of these two types. A redox reaction is one where electrons are lost or gained. In ion exchange, it's just a dance between ions. They switch off who they're dancing with. Redox includes synthesis, where two elements combine to form a compound. Synthesis means to make out of other parts. And of course, if you can put stuff together, you can also take them apart, and we call this change decomposition. Good. They're both redox reactions is because on one side you have elements that are not in a compound and therefore have no charge, and on the other side you have elements that are in a compound and therefore have charge. So since the charge changes, that means electrons are being exchanged. That's why it's an oxidation reduction reaction, redox. The third kind was called single replacement, where you take an element plus a compound and the metal replaces the metal, or if you've got nonmetals, the nonmetal will replace the nonmetal like that. And the reason why it's called redox is because you have elements that have no charge on one side but have a charge, not necessarily +1, on the other side. Elements that have a charge on one side but then don't have it on the other side, leaving the third ion as your spectator ion. Absolutely. Those would be redox reactions. Ion exchange is where you take two solutions, one ion from one solution and another ion, the opposite charged ion from the other solution. When they come together, bond so tightly that water can't break them apart and they precipitate out as a solid. And the other ions remain dissolved in water. Nobody's charge changes, therefore it's not a redox reaction. And you can identify your precipitate simply by going to reference table F, the solubility guidelines. So for example, all these guys are soluble. No, wrong table. Table F, there we go. All these guys are soluble except with these two, silver, lead 2, and dimercury 1, chloride, bromide, and iodide will not be soluble. But every other kind of chloride, bromide, and iodide will be. Same goes with sulfate too. Silver sulfate, calcium sulfate, strontium sulfate, barium sulfate, lead 2 sulfate, insoluble. Every other sulfate is soluble. These guys are all insoluble, except when combined with one of these guys, which are always soluble. Okay, so this will tell you which one is your precipitate. Whichever one is insoluble will be your precipitate and fall out. Yes?
That last one's also a double replacement reaction.
This one is called double replacement, absolutely. Ion exchange or double replacement. Yep.
Can we do like actual problems like that? Like insoluble?
Okay, so let's suppose we had NaCl plus AgNO3 forms NaNO3 plus AgCl. So let's see if we can figure out which one is the precipitate. Na is a group 1 ion and it's never in a precipitate. And also it's got nitrate, which is again always soluble, never in a precipitate. So we know NaNO3 is going to remain dissolved. Chloride is usually soluble, but not when combined with silver. So that means this is your insoluble precipitate there. You're welcome. Anything else? That was a big one. Most outstanding. And what I like so far is the questions I got from period 3 and the questions I'm getting from you guys are different questions. Which means when they're all combined together to make this final video, it's going to be awesome. What's up?
So sorry for interruption. I just want to say thank you very much for everything.
Oh, you're very,
Yes,
very,
absolutely.
very welcome.
It's an awesome teacher. All right.
That's a Jay. Hey, Jay.
Hey, Jay. You take care of yourself and keep in touch.
I'll try my best.
All right. Where are you going to school?
I'm going to Daytona Beach, the Army ROTC.
Oh, that's right, that's right. Usually when they say I'm going to go to Daytona Beach, it's like, yeah! To join the Army. Oh.
Either way, I'm on the beach.
Enjoy.
Alright, thanks so much.
Yeah, that was really nice. Okay, next question. Explain in terms of the polarity of super or sugar molecules. Oh, why the sugar dissolves in water. Okay, this was actually a question taken out of an old Regents exam. It's actually very simple. It says, explain in terms of the polarity of sugar why the sugar dissolves in water. All you have to remember is this. Like dissolves like. Things that are polar will dissolve in polar solvents. Things that are nonpolar will dissolve in nonpolar solvents. Which one is water? Polar or nonpolar?
Polar.
Polar. Remember how I was able to bend it using the electrical charge? Oh, geez. Yeah, it's called the water saver faucet. It just spits the water out of the top. Remember when I bent the water with the electric charge?
Yeah.
Okay. That demonstrates that water is attracted to electrical charges. It's a polar molecule. And since water is polar, in order for sugar to be able to dissolve in it, sugar must be polar as well, because like dissolves like.
Why does it shoot the water off the top?
I have no idea. I don't know what the internal construction of this thing
Constantly
is.
sprays water back.
Yeah, exactly. It's doing it right now, and it's really annoying.
That's not spraying. I mean, like you turn it on and it sprays it. Like that coming out the top. Whichever one's over here does it all the time.
What's even crazier is turn on one over there and another one over there goes on.
No way.
Yeah, there's some interconnections. Let's see. Was that the weirdest thing? Okay, next question. Albert Einstein called it spooky action at a distance, but he actually meant that if you've got two quantum entangled particles and you make a change to the state in one, the exact same change will happen in the other particle, no matter how far apart they are, even exceeding the speed of light. Yeah?
How many ones symmetry is like polar? Two.
Polar has one.
Non-polar has one, non-polar.
Write it down, put it in the box. It is, and we will get to it, I'll guarantee it. Okay, next question. Weight, protons, neutrons, electron, and charges.
Oh, that's mine, sorry.
Okay. Let's take a look at reference table O, because all that information can be found right there.
Oh.
Exactly. In reference table O, the top number is the mass, the bottom number is the charge. So if you want to find the mass of an alpha particle, boom, there it is, 4. So if you want the mass or charge of protons or neutrons or electrons, beta particles are also known as electrons. 0, -1, charge of -1, charge of +1, charge of 0, mass of 0, mass of 1, mass of 1. So you can always look it up on reference table O if you forget it. That's why the atomic mass is the number of protons and neutrons together, because they both weigh 1 each.
So what are beta particles equal to?
Beta particles are electrons, which is why they use the symbol E for it. And positrons are also known as anti-electrons, or electrons with the opposite charge that they normally should have. Yep. Alright, next question. Voltaic cells. 3rd out of 4 questions. Voltaic cells. Not really a question, but in essence, what's going on with a voltaic cell is we look up on reference table J 2 metals that we can use as electrodes. So for example, let's use the metals magnesium and zinc. Magnesium and zinc. The reaction is magnesium reacts with zinc nitrate to form magnesium nitrate plus zinc. Okay? Single replacement reaction. In this reaction, magnesium goes from 0 to +2. It's oxidized, making it the anode. The zinc goes from +2 down to 0. It's reduced, making it the cathode. So when you set it up, instead of reacting the magnesium directly with the zinc, because the electrons would just transfer immediately, what you do is you put the strip of magnesium, the more active metal, into one beaker, and you put the zinc nitrate into the other beaker as a solution. To allow electricity to flow from one to the other, we need to put a strip of zinc metal in here. And the reason we use zinc is because zinc will not react with itself, but will conduct electrons down to the zinc nitrate. We put the magnesium in a solution of magnesium nitrate because magnesium will not react with itself, and we need an electrolyte in here to conduct electrical charge. You hook the two half cells up to an electrical device that you want to power. That's called the
Load.
And it can be anything that you want to power with electricity. And to complete the circuit, we connect the two solutions with a salt bridge, the purpose of which is twofold. One, it allows for the completion of the electrical circuit, and two, it allows for the solutions to remain electrically neutral, because as magnesium becomes magnesium +2, that puts an excess of positive charge in here, so negative ions come out to take their place, so that you have electrical neutrality in there. And as the zinc nitrate, as the zinc +2 leaves this solution, positive ions come out of the salt bridge and take their place to maintain electrical neutrality in that half cell as well. Electrons will always go from anode to cathode through the wire and through the load on fire. And the anode is always designated as the negative end of the battery. This way you always plug your battery in correctly to the device you're trying to power.
Start at zero.
Electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode, reduce the cations, and the anions go through the salt bridge back to where? Whee! Okay, good deal. And that's voltaic cells. In a nutcase, nutshell. Yes, ma'am.
Should the load, don't we need to know that too?
The electrolytic cell?
Yeah, that.
Write it down, put it in here.
I don't think I wrote it right.
Oh, I'll find it when we get to it. Okay. All right, next question. Next question. Can we go over bonds types? Yes. Very simple. There are only two types of chemical bonds that result in compounds. And they're called ionic and covalent. And there are no other types that make compounds. If you have a metal and a nonmetal, metals have very few valence electrons. Nonmetals almost have a stable octet. Metals have a low electronegativity. Nonmetals have a high electronegativity. So the electrons get pulled from the metals to the nonmetals. This makes the metal have a positive charge and makes the nonmetal have a negative charge. And the two opposite charges attract each other, forming an ionic bond. Okay? Ionic bond. A bond made from ions. charged particles. Yes?
Is that diagram the Lewis dot diagram?
It is the Lewis dot diagram for an ionic compound.
How did you do it on the regions we took? That weird one, like, you told us not to.
Hydrogen sulfide. Okay. If you've got two nonmetals, nonmetals both have high electronegativity, which means they both can't gain or lose electrons. Their only option is to share their unpaired valence electrons in what's called a covalent bond, which is a pair of shared electrons. Now, the molecule that you had to do on the Regents exam was hydrogen sulfide. Both hydrogen and sulfur are nonmetals. Sulfur has 6 valence electrons, with room here and here for hydrogens to share a valence electron, giving you a nice, do you remember what the shape of this molecule is? Bent, exactly. Shapes again? Linear, bent, pyramidal, right, pyramidal, and tetrahedral, right. Absolutely. Tetrahedral is what shows up most often. And in fact, usually it's going to be what is the bond arrangement around carbon, and it's always tetrahedral. And that's what's going to show up most often. Okay. That's ionic versus covalent. Okay, next question. When pH colors change, what does the range mean? For this, we have to go to reference table M. That's M as in magnificent. Okay. Here's what the range means. Let's take, for example, methyl red. Let's say this is a pH of 0 to a pH of 15. Methyl orange is red, right up to a pH of 3.1, at which point it begins to change to yellow, and the color change is complete at a pH of 4.4. In between these two, it's orange. So a question might ask, what's the color of methyl red in a base?
Yellow.
Exactly, because bases have a pH higher than 7, and from above 4.4, they're going to be. So that would be a typical application of this particular question. And that's what the range means on reference table F. Any questions on this? Okay. Next question. Electrolytes. Not exactly a question. I will turn it into a question. What is an electrolyte? Okay. We defined electrolytes in our last review session. Does anybody remember the definition of an electrolyte? Not an example of an electrolyte, but what is an electrolyte?
Something repeatedly shared, like
No.
twice as much hydrogen
No.
as carbon.
No.
Something that is no.
Anything that dissolves in water, breaking up into ions, which can carry electrical charge. Anything that dissolves in water to form ions. This is one of the 50 frequently forgotten fun facts. It's probably the most forgotten of all the 50 fun facts. If we take, for example, C6H12O6 and we dissolve it in water, is this going to break up into ions?
Yes.
Is it made of metal and non-metal?
No.
No, therefore it will not break up into ions. This is an example of a non-electrolyte. Something that when you dissolve in water will not conduct electricity. Alright? What about this? NaCl, dissolve that in water. Will that break up into ions?
Yes.
It'll break up into the sodium ion and the chloride ion, each of which can carry electrical current, since they're moving through the solution. What about this? NaOH. If we dissolve that in water, will that break into ions?
No.
Darn tootin' it will, because it contains a metal and non-metals. It's ionic, meaning it'll break up into a sodium ion and a hydroxide ion, carrying electrical current.
They're supposed to have charges?
When you dissolve them in water, they break up into their individual
So they
ions.
don't.
Hang on just 1 second. I'll show you something. It's not a decomposition reaction. Okay. Here's the difference. Okay. Sugar is a polar molecule, which is why it dissolves in water. And in a polar molecule, you don't have separate ions. The molecule is one unit. The atoms actually become part of each other, and you can get partially charged ends, but you can't actually ever split this molecule into individual ions. So anything that's molecular, anything that's covalently bonded, strictly made of nonmetals, that's going to be a non-electrolyte. But ionic compounds look like this. All right, we've got sodium, and we have chloride or hydroxide. Okay? Metal, non-metal. When you dissolve this in water, the water molecules attach onto the ions, and the motion of the water molecules pulls the ions apart. But they're still able to move around in solution, meaning they can carry their electrical charge from one place to another. And that's what an electrolyte is. Okay? There is one exception to the covalent bond non-electrolyte rule, and that only exception are acids. HCl, dissolving it in water, guys, the definition of acid is any substance which, when it dissolved in water, yields H plus as the only positive ion in solution. Meaning there's also going to be a negative ion, and if you've got ions, they can carry electrical charge. These are all electrolytes. Acids, bases, and salts are all electrolytes. And when dissolved in water, will break up into ions, electrically charged particles, able to move and carry their electrical charge with them wherever they go. Anything else on this? Think about it. Think about how easily some of you forgot electrolytes between last time and this time. This is something you're going to want to make sure you do plenty of as part of your review for your Regents exam. Okay. Next question. We still have plenty. That's wonderful. Chemical bonding. Been there, done that. Next up. Different types of reactions. Been there, done that. Same handwriting. Next question. Sublimation. They also put PE diagrams. We've already done that. Let's talk sublimation. It is. And there's a reason for it as well. Polar molecules. Okay. All right, guys. If you've got a polar molecule, you're going to have fairly strong attractive forces between the molecules because the positives and negatives will attract. Which means that typically when you melt them, they'll still kind of hang around near each other. I mean, they're able to flow. They're not locked in a crystal lattice anymore. They are able to flow, but they're still attracted to each other to make a liquid. Solid to liquid would be melting. Nonpolar molecules, on the other hand, have no permanent positive or negative ends, which means any attractive forces between them are going to be really what? Really weak, right? If there's no positive or negatives to attract, then the amount of attraction is going to be really weak. If you cool them down enough, they can form a solid, but when you heat them up, the attractive forces are so weak that they're not strong enough to hold them together to form a liquid. As soon as you heat them up, they turn into a gas. And that's called sublimation. And it happens with the substances carbon dioxide. Guys, carbon dioxide is nonpolar, and it also happens with iodine, I2, because again, that's a nonpolar molecule. It also happens with mothballs and some other molecules as well. But those are the two big ones. Solid to gas, which means the gas can come together. If you cool it down, it'll turn directly into a solid again. It won't go through a liquid phase because the attractive forces just aren't strong enough to hold it as a liquid.
What about nitrogen?
Nitrogen will also will not undergo sublimation. Well, it depends on the... See, the phase depends on not only the temperature, but also the pressure. So, for example, where's my little can of... I don't have it here. Wait, here's something here. I've got liquid butane in here. Butane is normally not a liquid. Butane is the kind of thing that will turn directly from a solid to a gas under normal atmospheric pressure. But under higher pressure, it will turn into a liquid. So the phase change temperature and what phase you get is also determined by the atmospheric pressure it's at. In space, pretty much everything is going to turn directly from a solid to a gas. The reason we form a liquid is because we have air pressure sitting on it, saying, okay, we've weakened the attractive forces, but the air pressure itself is still holding it together as a liquid. In space, where there's no air pressure, pretty much everything will go from a solid to a gas if you heat it up enough. There are some exceptions. For example, metals, heavier elements, they will liquefy, which is one of the reasons why, early on in the solar system, you could still have molten rock around the Earth even though there was no atmosphere, and it wouldn't turn directly into a gas. Yeah?
What's gas to solid?
Deposition. Think about it, deposit. So a gas deposits as a solid. Yep. Okay, anything else on this? I'm glad I was able to use these for more than just the one thing. Okay. Next up. Why are you such an awesome teacher? T-E-A-C-H-E. Question mark, smiley face.
I'm gonna go with Lucia.
Okay, why am I such an awesome teacher? Because you are such awesome students.
Who's your favorite student? And you can't say all.
I don't play favorites. Okay. Difference between voltaic cell and the build of a battery. Okay. A voltaic cell is a battery. So there's no difference between them. A voltaic cell and a battery are the same thing. Okay. Next up, combustion. All right. You want combustion? I got combustion. Look at reference table I. The first 6 reactions on reference table I are combustion. You take an organic compound, react it with oxygen, produces carbon dioxide and water vapor, and a whole boatload of energy, which is why we use them as fuel. The one down here, C6H12O6 plus 6O2, is what we use to live. Cellular respiration. And this is the energy right here that can either make your muscles move or be stored as fat. depending on how active you are.
H18. That seems like a better thing to use.
This right here is gasoline. And that's why we use it as gasoline, because it packs a lot of energy into a little space. But remember that this is for burning 2 moles of gasoline. If you only burn 1 mole of gasoline, that's just about 5,500 kilojoules. And so that, it's still more than the others, but puts it more in line. Okay, next question. I tell you, I was just burning up to answer that last question.
Get it?
What does anonymous mean? How many licks does it take to get to the center of a Tootsie Pop? And Doctor Who?
What was the number to the universe?
Okay. All right. Anonymous means to be done without any attribution. In other words, we don't know who did it. How many licks does it take to get to the center of a Tootsie Pop? 3. 3 licks to get to the center of a Tootsie Pop. If you're familiar with the old commercial. Doctor Who, they actually said his name in the last season of Doctor Who, but not so you could hear it, and it ultimately led to the end of the universe, except he was able to get it reborn again.
What was the name?
No one got to hear it.
Wait, what?
No, who? Next up! Can you go over hydrogen bonds? I was tempted to write the word hydrogen bonds on a piece of paper and step over it, because that way I will look on over hydrogen bonds, but I will refrain. Hydrogen bonds are the only attractive forces you need to know by name for the regions. There's no dipole, there's no London dispersion. All it is hydrogen bonds, where the H end of one molecule, which is partially positive, attracts to the N, O, or F partially negative end of any other molecule. For example, H2O, HF, HCl. No, not HCl, because HCl has H on one side, but not NO or F on the other. So that is hydrogen bonds! Hydrogen bonds! H on one side, NO or F on the other. It's really polar, and it attracts like a mother. Dipole attractions repel. I love hydrogen bonds so well! Next up. What is an isotope? Excellent. What is an isotope? Okay. Guys? Gentlemen?
We're talking about science.
Yeah, okay. Guys, please. These are isotopes. They're atoms of the same element that differ in their atomic mass. There are 3 isotopes of hydrogen. Hydrogen with a mass of 1, hydrogen with a mass of 2, hydrogen with a mass of 3. They all have the same number of protons, but the number of neutrons is different. There are several isotopes of helium. Helium, let's see if I can zoom in further on this and focus. Helium-5, helium-6, helium-8. Okay, they all have 2 protons. This has 3 neutrons, this has 4 neutrons, this has 6 neutrons. So isotopes are atoms of the same element because they have the same atomic number, but their masses are different because they have a different number of neutrons. In fact, this whole thing is a table of the isotopes, because it lists all the isotopes of all different elements. Neon 17, 18, 19, 20, 21, 22, 23, 24. All have 10 protons, but the number of neutrons is different, and therefore their masses are different as well. Those are isotopes. By the way, for attribution, that was a CRC Handbook of Chemistry and Physics, 64th edition, 1983-1984. And are there any formulas we should know that aren't on the reference table? No. They will be given to you if you need them, but I've almost never seen it happen. Math is not a big issue on the Regents exam. It's really not. Particularly not to the level that we did it this year. Next question. One way in which the United States Constitution created a... Wrong side. Just a natural decay problems, please. Okay. I'll do one of each kind based on reference table N. Okay. So we'll do carbon 14, calcium 37, and we'll do francium 220. In natural decay, hooray! An unstable nucleus breaks down to form a decay particle, and the element turns into a new element. In the case of carbon, a beta particle, 0, negative 1e, is given off. In the case of calcium-137, a positron, I think that's right, isn't it? Yeah, a positron, 0, positive 1e, is given off. And in the case of francium-220, an alpha particle, 4/2he, is given off. And if you don't remember what these symbols are, you can always go to reference table O and look up your alpha particle, your beta particle, and your positron. The other piece of information we need are the atomic numbers. The atomic number of carbon is 6. The atomic number of calcium is 20. And the atomic number of francium is 87. Now, to find the new element that we get when we vomit out this particle, we have to obey the law of conservation of mass and the law of conservation of charge. The law of conservation of mass says that we have 14 on the left, we've got to have a total of 14 on the right. What is the mass of our new element? 14. We've got a mass of 37 on the left, we need to have a mass of 37 on the right. What's the mass of our new element? 37. We've got 220 on the left, it has to be a total of 220 on the right. 4 plus what? 216. The law of conservation of charge means that the atomic number has to add up to the same thing on both sides. We've got 6 on the left, it needs to add up to 6 on the right. This needs to be 7, because 7 and negative 1 is 6. We have 20 on the left, we've got 1 on the right, so this needs to be 19. We have 87 on the left, we have 2 on the right, meaning this has to be 85. Now, when the atomic number changes, it changes what element you have as well. Element 7 is no longer carbon, it's nitrogen. Element 19 is no longer calcium, it's potassium. And element 85 is no longer francium. Element 85 is... What?
Element 87.
Yeah, element 87 is francium, but that's not what we have anymore. Element 85 is astatine, At. So astatine, potassium, and nitrogen. And that is how to do natural decay equations. Exactly. Start with your unstable nucleus, determine what it's vomiting out, and what the new, more stable nucleus is going to be. Okay, any further questions about that? Okay. Next question. State the number of electrons shared between the carbon atoms in one molecule of the reactant ethene. This is taken directly off of an old Regents exam. So I'm going to draw ethene for you, and then we'll take a look at how many electrons are shared. This is a molecule of ethene. It has single covalent bonds between the carbons and the hydrogens, but a double covalent bond between the two carbons. How many electrons are involved in a single covalent bond? Like a handshake, 2 electrons are involved in a covalent bond, a shared pair of electrons. So how many total electrons are shared in a double bond? 4. 2 for each of the bonds involved. That would be 4 electrons in a double bond. If it was a triple bond, how many electrons are we talking about? 6. Exactly. Next question.
Thank you.
You're welcome. What is the difference between fusion and fission? Watch the video. Next question. Voltaic cells. Watch the video. Next question. Say this in a creepy voice. The Dark Lord shall rise once more. Next question. What are the different masses of protons, electrons, and neutrons? Reference table O. The next question.
Can't block that out with Rosengarten.
How a voltaic cell works. Done that? Next
Can
one.
you keep the creepy voice in there?
Of course.
Okay.
Dr. Breedmacken says, Merry Christmas. Next question. I'm glad I saved these till last.
Oh my god. Or we just put them in.
Can you go over what the two numbers before an organic compound mean, i.e. 1,2-propanal? Okay. The example is wrong, the question is very valid. Here's the deal. If you've got an alkane, for example, 5 carbons, this is pentane. You don't need any numbers because you've just got 5 carbons single bonded with hydrogens. You don't need to identify anything. But if you put anything on this, for example, a chlorine, chlorines can be put anywhere on this molecule. So the only way to tell where the chlorine is to say its position with respect to the end it's closest to. This would be 2-chloropentane. This would be 1-chloropentane. This would be 3-chloropentane. This would be 2-chloropentane because now it's closer to the left side, the right side, so we count in from that side, and this is 1-chloropentane. If you've got more than one, for example, if I've got 2 chlorines, this would be 1,1-dichloropentane because we've got 2 chlorines both on the first carbon. If I had a chlorine there and there, it would be 1,2-dichloropentane. If I had chlorine there and there, it would be 1,3-dichloropentane. So the use of the number is to tell you where you put the thing that's not a carbon or hydrogen. You can tell whether you need to put a number by looking at reference table R. Reference table R, if there is a number in the example, then you have to use a number when you name it. Yes?
Say the seal was over 1 more, would it be, you would keep counting like right to left, right? You can't just change.
Okay, when in doubt, you've got 2 choices. It's either 2,5-dichloro or 1,4-dichloro. Whichever one will add up to the lowest number, that's the one you go with. 1 plus 4 is 5, 2 plus 5 is 7, so we go 1,4. Yep. Whichever is going to give you the lower total. So for example, for an aldehyde, we wouldn't actually need to put a number in front of it. But for a ketone, we would need to put a number to say where it is. In this case, double bond oxygen is on the 2nd carbon end, 2-pentanone. And that's where you use Roman numerals in organic compounds.